Welcome back everyone. I am Saptaparni from BioLive. Hope all of you are doing very well. In today's video we are going to discuss about allosteric modulation of enzymes and its effect on Km and Vmax. Okay. This video is going to be useful for NEET aspirants, SIR Life Science NEET aspirants and all the UG and PG students of zoology, botany and biochemistry. So see, if this is an enzyme which is obviously an allosteric enzyme, it has two sides. One is active site, another one is allosteric site. In the active site, substrate binds, and in the allosteric site, either activator or inhibitor may bind. Okay. And upon binding in the allosteric site, the activator or inhibitor changes the 3D conformation of the active site. Okay. In case of activator, this change in the active site helps in binding with the substrate. Okay. So this kind of reaction is known as positive cooperation. On the other hand, if inhibitor binds to the allosteric site of any enzyme, then that also changes the 3D conformation of the active site, and as a result substrate is dissociated and the velocity of the enzymatic reaction gets decreased, and this kind of reaction is known as negative cooperation. Okay, so as a whole we can say that some enzymes are either activated or inhibited by binding with a low molecular weight ligands, which are known as either activators or inhibitors, and collectively as modulators or effectors to the allosteric site of the enzyme, and that is how they either positively co-regulate positively cooperate the enzymatic reaction or negatively cooperate. Okay, and those enzymes with the allosteric binding sites are known as allosteric enzymes. Okay, and the activators and inhibitors collectively called modulators, regulators or effectors. Okay, now one question may come in your mind that how does the allosteric modulated enzymes follow sigmoid kinetics? Okay, see here in this we can see, in this graph we can see the x-axis represents the substrate concentration and the y-axis represents the velocity of the enzymatic reaction. The Vmax represents the maximum velocity that can be achieved by any enzyme. Okay, now if there is no allosteric modulation, okay, there is no allosteric modulation present in case of any enzyme, then the enzyme follows normal michaelis menten kinetics and it forms a hyperbolic curve that we have learned earlier. Okay, so in case of no modulation, the curve is a hyperbolic curve and it follows the michaelis-menten kinetics, normal michaelis-menten kinetics. But if there is allosteric modulation in the enzyme, that means the allosteric site is present and activators and inhibitors can bind to those sites and positively or negatively cooperate in the enzymatic reaction, then the graph changes into a sigmoid shape. Sigmoid shape means S-shaped curve. Okay, and the reaction is known as heel sigmoid kinetics. This type of kinetics for allosterically modulated enzymes are known as heel sigmoid kinetics. Now, why there is a change in the shape of this curve? See, in case of allosteric modulation, we can see at the early stage of the enzymatic reaction, the substrate binds very slowly with the enzyme. That is why the initial velocity is very less. Here, the initial velocity is very less. But when the modulators bind at the allosteric side, the velocity starts to rise and as a result the S-shaped curve is formed. Okay, but in case of michaelis-menten kinetics, the velocity and the concentration of substrate and the velocity of the enzymatic reaction is almost directly proportional. That is why this hyperbolic curve is formed. Okay, now there is a slight difference in michaelis-menten equation and Hill-Sigmoid kinetics equation of allosteric modulation. In michaelis-menten equation, we know that V naught equal to Vmax into S by Km plus S. Okay, but here V naught equal to Vmax into S to the power n divided by Km prime plus S to the power n. Okay, Km prime is the new Km value for the allosterically modulated enzymes. Okay, and n represents the number of substrate binding sites, okay, active sites or allosteric sites, and the type and strength of reaction there. Okay, always remember that n cannot be 1. Okay, if n equal to 1, that means no allosterism is present there. Okay, n can either be greater than 1, okay, that means there are more than one sites are present, more than one active sites or presence of allosteric sites are there where activators can bind, and n is greater than 1 is only shown in case of positive cooperation where activators bind to the allosteric site. And in case of n is less than 1, we can see that there is a activator site obviously, and obviously there is a allosteric site, but to the allosteric site inhibitors bind. That is why the overall speed of the reaction, velocity of the reaction gets down regulated or negative cooperation is seen. So here the n is less than 1. So in case of activators n is greater than 1, but in case of negatively regulated reactions the n is less than 1. Okay, remember that. Now, this is all about allosterism. Now, let's take an example. Acetyl-CoA, this is the substrate. When reacts with ATP, it forms malonyl-CoA. Malonyl-CoA is our product and ADP and phosphate is formed. Okay. And in this reaction, the enzyme is acetyl-CoA carboxylase. Now, this enzyme is allosterically modulated. It has an activator and also inhibitor. The activator is citrate and inhibitor is palmitoyl-CoA. Okay, so if anyone asks you an example of allosteric modulation with both activator and inhibitors, you can give this example. Okay. Now coming to the main part, the effect of allosteric modulation on the Vmax and Km value. So, see, there are two types of allosteric enzymes. Okay, one is K series enzymes and another one is V series or M series enzymes. In case of K series enzymes, we can see that Vmax remains constant. Okay, see here for both activators and inhibitors of these kind of allosteric enzymes, the Vmax remains constant. But the Km value changes. That is why this type of enzymes are called K series enzymes. If activators react to these enzymes, the Km value is down regulated. That means we know that the Km value represents the affinity of enzyme towards the substrate. So whenever the Km value is decreased, that means the affinity is increased. That is why the activators increases the affinity of substrate towards enzyme and Km value is decreased. Okay. And when the inhibitors bind, obviously the affinity of enzymes towards substrate is decreased. That is why the Km value is increased. Okay. So, in case of activators, Km value is decreased. As a result, affinity of substrate and enzyme is increased. But in case of inhibitors, the Km value is increased. That is why the affinity between substrate and enzyme is decreased. Okay. But in both the cases, Vmax remains constant. Okay. Let's take an example. The example of this kind of K series allosteric enzyme is phosphofructokinase 1, or we also call it as PFK1. It converts fructose 6-phosphate into fructose 1,6-bisphosphate. Okay, with the reaction of ATP. One extra phosphate group is added to the first carbon of the fructose. And here phosphofructokinase 1 enzyme is required. Now, it has an activator known as fructose 2,6-bisphosphate and an inhibitor ATP and citrate. So, fructose 2,6-bisphosphate being an activator will decrease the Km value. But inhibitors, that means the citrate and ATP, will increase the Km value. but in both the cases Vmax value will be constant, okay, or unchanged. See here, this is the graph of K series allosteric enzymes. This is the graph of inhibitors, the black one, okay, and the pink one with the activators, okay. In both the cases, you can see the Vmax value is constant, okay, the Vmax value is constant in both the cases. If activator acts or inhibitor acts, the Vmax value is constant. But the Km value is changing, okay. See here, for inhibitors, the Km value is higher than the activators, okay. So if the Km value is lower in case of activators, that means the affinity is increased between enzyme and substrate, and if the Km value increases when the inhibitor binds, that means the affinity is decreased between substrate and enzymes, okay. And what is Km value? Km value is the substrate concentration at which the half Vmax or the half of the maximum velocity is obtained by any enzyme, okay. So here the changes is present in the Km value but not in the Vmax value, okay. Now going to another series of allosteric enzyme. The second series is V series enzymes or M series enzymes. From the name, it is evident that in this type of allosteric enzymes, if activators or inhibitors bind, the V, that means the velocity, the initial velocity or V naught or maximum velocity or Vmax will change. In case of activators, the initial and maximum velocity increases, okay. But in case of inhibitors, the initial and maximum velocity decreases. But in both the cases, Km value remains constant, okay. Km value remains constant. So it is just the opposite of K series, okay. So let's take an example. So acetyl-CoA carboxylase is an example of K series allosteric enzymes. The activator of this is citrate and inhibitor is palmitoyl-CoA. So being an activator, citrate will increase both the V0 and Vmax, but palmitoyl-CoA will decrease both V0 and Vmax. But in both the cases, Km value will be unchanged or constant, okay. So let's take a look on this graph of V series allosteric enzymes. See here, this is the graph for inhibitors and this is the graph for activators. See here, the Km value is constant for both the graph, okay. But the Vmax value is changing. This is the Vmax value when inhibitor binds to this enzyme, and this is the Vmax value when activator binds. So in case of activators, the Vmax value is higher, but in case of inhibitors, the Vmax value is lower. And in case of V0, the initial velocity, you can also see the V0 of activator bounded allosteric enzyme is higher than the inhibitor bounded allosteric enzyme. And why Km or the substrate concentration at which the Vmax value is half is constant? Because see here, this is the substrate concentration of the inhibitor bounded allosteric enzyme, okay, and this is the substrate concentration of the allosterically modulated enzyme of activator bound at activator bound state. So Km value is constant, but Vmax value and V0 value is changing in case of V series in allosterically modulated enzymes, okay. So this is all about the allosteric modulation and how the K series and V series enzymes, allosteric enzymes modulates the Km value and Vmax value of any enzymatic kinetics. Okay, so I hope this video is clear to you, and if you find this video useful, don't forget to hit the like button and share it with your friends, and don't forget to subscribe to my channel for more such videos. Thanks for watching and happy learning.